Giddy up. Okay. So we are going to bust out rational functions. You will notice on this worksheet that you have that it says graphing simple rational functions. Okay? I'm going to kind of talk very little about that because if we learned how to graph simple rational functions, I could teach it to you and you would get it. But then you would forget it. Okay? Like it'd be one of those things that you would get it, you'd get it for a test or a quiz, but then next year if you were in some calculus class, you'd probably forget it. Because simple rational functions just don't happen very often. So I'm going to teach this going right into just what are the things that we need to know to be able to graph rational functions. And I think I'll be able to teach that in such a way that the stickability factor will be much higher. Okay? So first of all, this is a simple rational function. So you can write this down. Okay? And just like all of the other functions that we learned at the very beginning of this school year when I handed you that packet, and it had the parent function, and then it kind of broke it down, boom, 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 boom. Do you remember that? Okay, do you remember how HK kept popping up all the time? Okay? HK was either the vertex of a parabola, it was the vertex of an absolute value, it was the center of a circle. Okay, whenever you see HK, it's telling you like either the vertex where something is centered. And the reason this is called a simple rational function is because it's the only rational function, the way you could write a rational function where it gives you HK, comma, shnikes. Okay? Do you guys remember also on the first quiz or test, the only thing that I said that you needed to know about a rational function was how to graph its parent function. Do you remember this? Head noddage yay, no noddage. Okay? Do you remember what this looks like? So if I just graphed the parent function of a rational function, let me step back. A rational function just means it's a function where you have a polynomial in the numerator over a polynomial in the denominator. Okay? That's all it means. And generally speaking, Alejandro, what would you say? Do you think you know what it looks like? Nope. So do you guys remember? Anyone? Okay. The parent function just looks like that. Okay? It has branches in the first and third quadrant. Okay? The parent function is the function before you do anything to it, before you shift it, before you up, down, right, left, big, small. Like when we were graphing a parabola, that's the parent function. That's the parent function of a parabola before you do anything to it. That's just the general idea of what a function looks like. Does that make sense, Gracie? Okay, so if you look at number 2 on here, okay? If you look at number 2, that's, I guess, going to be the first one that we just kind of do together. All right, so according to what I just shared with you, because this is a simple rational function, it's called such because it tells us the HK. So what would the HK of this graph be? 1, 1, correct? HK. H is what follows the minus sign, and then K is the constant that's being added. Okay? So if that's so, then that means when we start to graph this bad boy, that HK is 1, 1, which means that instead of this thing going in the first and third quadrant, it's going to be at 1, 1. So basically, there would be the vertical asymptote is going to be here. The horizontal asymptote is going to be here. And so before I even start to plug in points, I know that this graph is going to look like this. Does that make sense? And what I'm saying to you is I really don't think that this kind, a simple rational function, it just doesn't happen very often. You don't see it very often. And if you don't see something very often, then you don't use it. So even if I taught it to you right now, if I asked you in a year from now, I don't think you would remember this. Okay? So I'm going to go right into just how do we graph rational functions, period. Okay? And we're going to start talking about that today. And everything that we do today is going to be review, meaning I know you've seen it before. Okay? So we're going to talk about how do you find vertical asymptotes? How do you find horizontal asymptotes? How do you find x-intercepts? How do you find y-intercepts? Those are all things that I know that you know how to do. Then, when we start getting into these tougher rational functions, we're going to be finding things called removable discontinuities. We're going to find slant asymptotes. So we're going to build off of things that I know you've already seen before. So today, it's just all about bringing back all of the things that you once knew in Algebra 2. We're going to spend one day with that. Okay? So the first thing I'm going to do is I'm going to write this truly as a rational function, which means one polynomial over another, not two separate terms. Okay? What would be the common denominator between these two terms? Class? Oh yeah, why, Mr. Lothrop, that would be the quantity x minus 1. So, x minus 1 is the common denominator. What do you have to multiply this by to get the common denominator? Nothing. So I don't multiply the top by anything either. What do you have to multiply this by to get the common denominator? X minus 1, so I do the same thing on the top. Everybody good with that? Now I just simplify in the numerator. I can just drop the parentheses, and I'm going to have x plus 3 over x minus 1. And that is what y equals, or f of x equals. Does that make sense to every single one among you? Okay? Because 4 minus 1 is 3. Why couldn't you factor out the x minus 1? Where? Here? Because there's no x minus 1 in the first term. All I'm doing is simplifying an expression, right? Why can't you cancel out? Because you can't cancel across addition, right? That would be canceling across addition. Is that what you were saying? Okay. Okay. Yeah, you can't cancel across addition. Bad. Can't do that. Do you know why you can't do that? Or, just because you can't? Look at this real quick. 3 plus 6 over 3. Clearly, 3 plus 6 over 3 is what? What is it? 3. It is 9 over 3, which is 3. And if I go, ooh, Ganage, I think I see Ganage here. 3, gang. Now, what is it? Oh, poop. And we knew the answer was 3. That's why you cannot cancel cross addition. Okay? All right, so we're back on this now. So we took the time to rewrite this thing so that I've got rational functions. Okay? Now we're going to start just answering a bunch of questions with this. And I want to keep this up here, so I'm going to erase all this stuff. And this is what you guys will be doing on your investment. Okay? So before we start to graph these, we're just going to start by saying, okay, what is the x-intercept? Well, we know an x-intercept, that is, where it crosses the x-axis, is going to be when y is 0, right? An x-intercept happens when the y-coordinate is 0, right? So if I want to find an x-intercept, I'm going to substitute 0 in for y. When I go over to this function, and if I substitute 0 in for y, the only way y would be 0 is if this numerator is 0, right? Because 0 divided by anything would give me 0. Does that make sense? So if I want to find the x-intercept, I'm just going to take whatever the numerator is, and I'm going to set it equal to 0, because that's when the function's value would be 0. So I know that there's going to be an x-intercept at -3. Can I get an aha? Aha. Okay, next, I'm going to find y-intercept, if it exists. Y-intercept is the easiest one of all, because a y-intercept, something's going to cross the y-axis when x is 0. If I just stick 0 in for x, what is y? -3. Everybody with me? Okay. So I found, why don't I put this stuff on here while I'm doing it? Oh, were they both -3? Okay, what's your question? Because if you put 0 in for x, you would have 3 over -1, which is -3. What was the other question? Okay, this is coincidental that they're both -3. Okay, it's just a quinky dink. Doesn't normally happen. I thought I made a mistake because we got -3s. Okay, so let's do this. X-intercept is at -3. Y-intercept is at -3. Okay? The next thing we're going to ask is this question. And that's, of course, saying va, which means are there any vertical asymptotes? Vertical asymptotes happen when the function is undefined. Okay? Vertical asymptotes happen when the function is undefined. So again, I'm over here looking at this representation of our function. It's undefined when the denominator is 0, correct? Okay? As a matter of fact, that also, Andrew, determines the domain of the function, because the domain of a rational function is defined everywhere. So it's all real numbers except when the denominator is 0. Does that make sense? Okay? So the vertical asymptote, like I said, happens when the denominator is 0. So I just set the denominator equal to 0, and I know that there will be a vertical asymptote at 1. And oh my, look at that. We had a vertical asymptote at 1. That make sense? Okay. All right, here's the next question. And this is the one is at 1, and that's exactly what I just put up here, right? Okay. The next question we ask is, which of course is asking, does a horizontal asymptote exist? Okay? Here's where you got to listen like a champ. I know that you guys have learned this, but I think we need a little a refresher. Okay? And I want to teach this in a way that it isn't something that you're memorizing, it's something that makes sense. So listen like a champ, because in a year from now, if it makes sense, you're going to remember it. If you memorize it for a test, you're going to be like, oh yeah, I once knew that. Okay? When you're trying to identify a horizontal asymptote, okay, you're going to want to look at this representation of the function. Okay? This rational function, because we just have one polynomial divided by another. Okay? You compare the degrees of the degrees of the numerator and the denominator. What is the degree in the numerator? What is the degree in the numerator? Do you know? 1. Okay? It is the term that has the highest exponent, is the degree, right? Okay? What's the degree in the denominator? 1. Right? Okay, now, if the degrees are the same, so a horizontal asymptote, think about what a horizontal asymptote is, okay? If a horizontal asymptote exists, that means that when you stick in huge numbers for x, the function's value is going to just approach that number, right? It almost seems counterintuitive that you could put in 1,000,000 and it approaches, in this case, it looks like it's approaching 1, doesn't it? Almost is like, what? Okay? But if you think about it, if you put in some huge number like 10,000, 100,000, 1,000,000 into this function, This term and this term are going to dominate the function. Like when you start putting in like a million, does this plus 1 or minus 1 going to have any relevance to the value of the function? No. Okay? So you compare the degree in the numerator with the degree in the denominator. So it's x over x. Well, does it matter how big the number is if you're saying x over x? What is x over x? 1. So when the degrees are the same in the numerator and the denominator, there will be a horizontal asymptote at the ratio of their coefficients, which in this case is just 1 over 1. Does that make sense? Okay, and that's the idea. Is I almost guarantee that most of you learned this in Algebra 2, and you memorized it, but you had no idea why it was the way it was, if you're like me when I learned this the first time. Okay, does that make sense? All right, now let's just look at the other scenarios while we're talking about horizontal asymptotes. What if, and I'm not changing this problem, I'm just changing it to make a point. What if the degree were bigger in the top than in the bottom? Would a horizontal asymptote exist? No, I mean, think about it. Now, this term is going to dominate the function, right? The bigger the number you put in, isn't the function just going to keep getting bigger and bigger and bigger and bigger? So it's not going to approach a value. It's just going to, the bigger the number, the bigger the value. It's not going to approach, it's not going to have a horizontal asymptote. It's just going to keep getting bigger the bigger the number you put in. Yes, Sarah? Yeah, so if the degree is bigger in the top, it would be irrelevant as to what these coefficients are. Because basically that term is just going to, because you're squaring a million, like if you put a million in for x, a million squared is just so much bigger than a million that that term just dominates the function, and it's just going to keep getting bigger. Okay? Does that make sense? So if the degree is bigger in the top, there is no horizontal asymptote. Let's look at the other scenario. What if the degree is bigger in the bottom? So let's say, what do you think, Emily? There will be a horizontal asymptote at 0, okay? And I want this to make sense. I don't want it to be something that you memorize. Won't that term take over the function when you start putting in huge values? Okay? And if you think about it, 1 over 1,000, 1 over 10,000, 1 over 1,000,000, 1 over 1,000,000,000, what are you getting ridiculously close to? 0. So if the degree is bigger in the bottom, there will be a horizontal asymptote at 0. That make sense? Hopefully that's review. Okay? That's something you guys did in Algebra 2. All right, let's get back to our question. So where's the horizontal asymptote? At 1. Okay, at y equals 1. Because the degrees were the same, so it's happening at the ratio of their coefficients, which was 1 over 1. Okay, so there it is. Now, guys, now check this out. This is huge. We had these 2 points. That was our y-intercept. This is our x-intercept. Vertical asymptote, horizontal asymptote. Okay? Doesn't it just make sense? Let's see, I'm going to just go to a different color. Like, this is exactly what this graph is going to look like. Because we had those 2 points. We knew that the function had to approach the asymptotes. So there's that branch, if you will. It's called a branch. All right? Now, here's my next. This is huge. Okay? When we found x and y intercepts, particularly x-intercepts, not only did we find that this is an x-intercept, we also know there are no other x-intercepts. That's almost more helpful than finding the x-intercept itself. Because when I go to graph this thing to the right of this vertical asymptote, I know the function's not going to look like this. Because if it did, there would have been another x-intercept. Does that make sense? So I know that this graph is going to do this. Because there were no other x-intercepts, so it couldn't have done the other one. Does that make sense? And then you just like plug in a couple values and like we did here with the y-intercept and x-intercept. So if I put in, I don't know, so if I put in 2, that's right to the right of the vertical asymptote. If I put in 2 into this function, I'd get what? 5 over 1? So at 2, the function's at 5. Blam. Which is right in line with what we were saying. Okay? And I would say you should probably plug in one more point. Does that make sense? All right, let's just do one of these. Let's bust out one more of these together, and then so the domain, so here's our graph, right? This was our graph. The domain is all real numbers except what? It's everything but where the vertical asymptote is, right? The domain, the x's. So the domain would be all real numbers except x cannot equal -1. What would the range be? All real numbers except y cannot be 1, where the horizontal asymptote is. Isn't this the horizontal asymptote? So it would be everything but y cannot equal 1. Yeah. Yeah, so you can just say all double bar, finish the R. That's all reals. It's kind of fun to make, and even funner to say. Double bar, finish the R. Okay, let's do one of these together. Let's do number 5. And then you guys can have the rest of the bell to just bust this out. No. No graph and calculator tour on these. But I don't think it's till like next Friday, if I remember correctly. We got a lot to learn. So basically all we're doing today is stuff that you guys already know, and then we're going to build off of that because there's a lot more to it than what you learned in Algebra 2. Okay, so what was the first thing we did? First thing we're doing is going to rewrite this thing so that it's just a polynomial over another polynomial. So let's do that. So the common denominator is going to be, talk me through this, people. X plus 1. What do I need to multiply the 3 by? Nothing. Minus 2. What do I got to multiply it by? X plus 1. And now I just got a slack, which of course is simplify like a champ. So I've got 3, distribute the -2. So it's going to be -2x plus 1 over x plus 1. Okay? Now before I start to graph this thing, I'll go ahead and make my axes, but we're going to just start answering a bunch of questions, and then as we answer them, I guess we'll put it on our graphs. Okay. What's the first thing? Yeah, so let's find our x-intercepts. We know happen when y is 0. We know that y is 0, the function's value is 0, when the numerator is 0. So I'm just going to take the numerator, set it equal to 0, solve for x. So there will be an x-intercept at 1/2, 0. Everybody good with that? And I'll plot that bad boy. Y-intercept. Y-intercept happens when x is 0. Just go to this, and it's a piece of cake. If you stick 0 in for x, what's it going to be? 1. 0, 1 is the y-intercept. Because y-intercepts happen when x is 0. So if you just put a 0 in for the x's, you're just going to be left with 1 over 1. Okay? So remember, we didn't just find the x-intercept. We know that they're the only x-intercept. So the graph will not cross the x-axis at any other places than 1/2. Okay. Next question. The vertical asymptotes happen when the function is undefined. The function is undefined when the denominator is 0. So I just take the denominator, set it equal to 0, and I know I've got a vertical asymptote at -1. Everybody good with that? So, blamage. Okay? Here's the tricky one. Horizontal asymptotes, we compare the degree of the numerator with the degree of the denominator. The degrees are the same, are they not? So the horizontal asymptote exists at the ratio of their coefficients, which is Schnei-Keys. What did you say, Will? -2, the ratio of their coefficients. The degrees were the same, right? They're both to the 1. So the horizontal asymptote is at the ratio of their coefficients. So y equals -2. That makes sense, everybody? Okay, y equals -2. So, okay. So I would suggest to you, I'm done finding stuff. I would say I know what this graph is going to look like without plugging any points in. Doesn't it have to do this? Because it has to approach the asymptotes, right? Graphs have to approach the asymptotes when they get huge. And then to the left of the vertical asymptote, it can't be above the horizontal asymptote, because if it was, it would have another x-intercept, wouldn't it? You see what I'm saying? Like if it was to the left of the vertical asymptote, it can't be this, because it would have another x-intercept here. So I know before I plug any points in that it's going to look like that. Does that make sense? And then my insurance policy is I just plug a couple points in. So if I stick in -2, let's put in -2. That's to the left of the vertical asymptote. If I put in -2, what am I going to get? Right? -5, if I plug it in here. So -2, -5, and that just kind of confirmed what I already knew. Does that make sense? Okay, any questions before I turn this thing off? Something I didn't explain very well? Okay.